14.2, we're going to take a look at circuits, specifically circuits that are attributed to somebody's name that you've seen before. Do you remember when you saw this name before? Euler diagrams, and you even said it right, very well. And so, yeah, it is Euler. Euler was his name. It was back in section, I think it was 3.5 or something like that is the number. We were doing it like in the middle of truth tables and so forth. There were the diagrams that looked kind of like Venn diagrams, but they didn't have the big old rectangle around them. Do you remember that? It was a logic section that we did. So Euler was a mathematician, and he also worked a lot with geometry. Which is why we saw that geometric sort of approach to logic before. And this is also graph theory, a portion of geometry. And so we're going to talk first about what an Euler path and an Euler circuit are. So if you watched section 4.1, you would have seen what it meant to talk about a path and what it meant to talk about a circuit. But an Euler path specifically is a path that uses every edge of the graph exactly once. Okay, so it crosses all of the edges, and it doesn't cross any of them twice. That's an Euler path. An Euler circuit is a circuit. So circuit means it starts and stops in the same place, just like as if you were talking about circuitry, right? Like computer science-y stuff, right? It uses every edge exactly once, but it's a circuit. Okay, so it's got this exactly once business, just like the Euler path does, but it starts and ends at the same place. Now, not all graphs have these. Some graphs don't have Euler paths, some graphs don't have Euler circuits, or they may have a path, but they don't have a circuit, so they could have one and not the other, and they could have neither. These do not have to be present in a particular graph that you're working with. So we're going to take a look at a graph. This is the one we're going to start with. And we're going to consider whether or not the following listed sets of vertices in order are going to create an Euler circuit. So again, brief reminder, especially if you didn't watch 14.1, which I'm sure is not true for anybody, but just in case. The points are all called vertices. And when you connect a vertice with one of these line segments, it doesn't have to be straight, by the way. All the ones here are straight, but whether they're straight or whether they're curved, they're called edges. Okay? So what this is a listing of here is this lists going from one vertex to the other vertex. It just lists an ordering, like, like a to-do list, right? You're going to go from this to this to this, right? So it's an ordering of things. And we're trying to decide if it's an Euler circuit. So remember, circuit means it has to start and end in the same place. And it has to cross every edge exactly once. It has to cross every edge. So from the get-go, it does start and end at the same place, correct? You can see the A at the beginning and it has the A at the end. So it hits that kind of criteria. Our question really on this one, because we know it starts and ends in the same place, is whether it hits all the edges once. So what we're going to do is we're going to trace along the edges, and we're going to see if it does that. And we're going to do it in such a way that I hope I can erase it and do the next one so that it doesn't get confusing. So we're going to go from A to B, and then we're going to go from B to E, and then we're going to go from E to D, and we're going to go from D back to A. Is it an Euler circuit? No. Why?
It doesn't use all the edges.
Yeah, it misses quite a lot of them, in fact, doesn't it? It only has to miss one for it to fail, but it misses a lot. So this one is not an Euler circuit. Though it is a circuit, I'll write that down just as a reminder for us in a moment. And the reason is because it fails to cross every edge, right? But it is a circuit. I didn't actually have an example of a circuit in lesson 1, so now you've seen an example of a circuit here in lesson 2. Okay, is that all right? All right, we're going to actually do it this way. Oh, good grief. What did I do? Let's just get it again. All right, we're gonna try the next one then, okay? So on the next one, we're gonna cross through all of our corners that it lists as well. I actually could not do this one at all and not cross anything, which this one's gonna fail for lots of reasons. Spoil all the fun. It fails at the very beginning because of what? Doesn't start and end in the same place, right? It starts at A, it ends at G. So it's definitely not going to be a circuit. Okay, so it's going to fail for that reason. We're going to look for other potential reasons it fails as well. And the reason we're really going to do that is because the way these questions often show up in my math lab is they're multiple choice answers. And within the multiple choice answer, it will give you it fails to be an Euler circuit because, and it will list something. And you want to make sure that you know what are all the reasons it fails, or you might end up accidentally picking the wrong multiple choice answer just because you didn't pay attention to all the ways it failed, okay? So we're going to look for all the ways it failed. So we're going to follow them in order like I did before. We're going to start with A and go to B. And then B is supposed to go to C. And there's a problem with that. What is the problem with that? There wasn't an edge there to begin with, right? So I likened this in section 14.1 to the sidewalks. Like you had to walk on the grass if you did this, right? You had to get off the sidewalk and walk on the grass. Well, it can't be an Euler circuit. It can't be a circuit. It's not even a walk because a walk means you stayed on the sidewalk, right? I mean, that's the deal. So it fails from that. If you take a look at the next one, it fails too. Like C to D is another place where you're not allowed to do that, right? C to D doesn't work. D to E would have been fine, and so would E to G, but again, we wouldn't start and end at the same spot. And also notice, what else is a problem? I missed a lot of edges. I missed a lot of walking along the sidewalks, and I walked off the sidewalk, and it didn't start and end in the same spot. There's 3 reasons this failed. Yeah, it's not a circuit. We had already mentioned that at the beginning too, you bet. So that's going to be one of the things. So this one is not an Euler circuit. And we're going to list several reasons why. So 1, it's not a circuit. 2, what was it, the letter before? B. B to C, and C to D are not edges. Okay? And the third reason was what? Do you remember? Yeah, we missed many edges. Okay, does that make sense? We're just looking for all the ways it failed. I think that's all the ways this one fails. I think we got them all. Okay, you have one more on your list, but I ran out of space, so mine's on the next slide. Same picture. We're going to do the same thing. We're going to go in order. Okay, so we're going to go A to B, B to E, E to F, F to G, G to E, E to D, D to A, which if I stopped there would be a circuit, but it continues, right? It says after A, it says I'm going to go to E, and then E to C, and then C back to A. Okay, so what about this one? Yes, it worked, right? It did all the things it was supposed to do. Notice there weren't any sort of pieces that said that it couldn't, like I can only go across every edge exactly once, which I did. But there was a point that I crossed through more than once. It was A, right? I went back to A, and then I went around another little circuit and went to A again. That's okay. There's nothing that says I can't do that. So that's not an alarming or a concerning thing because that wasn't one of my things that was sort of disallowed. So this one is an Euler circuit. Okay, that good? All right, our next thing that we're going to take a look at is Euler's theorem. So Euler's theorem says, suppose we have a connected graph. Connected simply means, from last time, any point and any other point have some kind of a way to get from one to the other without going on the grass, right? Like over here, I promise I'll come back to this one again. I know it kind of messed up and I went from B to C, but I could have gotten from B to C. I just didn't do it the right way. I would have had to go through another location, right? So in order to get from B to C, and there not being a segment there, which there originally wasn't, I would have had to go from B up to E and then over to C. Okay, so connected just means that there's some way that I can get from one point to any other point. There's always a way to do it, okay? So if I have a connected graph, then the graph has number 1 says, if the graph has an Euler circuit, then each vertex of the graph has even degree. And number 2 takes that statement and it flips it around. And it says, if each vertex of the graph has an even degree, then the graph has an Euler circuit. So jot that down, and I want to make a really strong comment about this. It's simply not always true. Okay, do you remember back in chapter 3 when we were talking about logic and I showed a VeggieTale video? Okay, so if you weren't here, then you don't remember it because it's not something I can post on, on my Canvas stuff because it doesn't work like that. But if you weren't here, it's Silly Songs with Larry. Larry sings a silly song about monkeys and tails. That's what it was. And so he says things like, if it doesn't have a tail, it's not a monkey. Okay? And then he says something like, if it does have a tail, then it is a monkey, and he has a problem, right? So he has these sort of statements that they don't go both directions, right? That's the problem that he was having. So this is one of those statements that does go both directions. If this is true, then this is true, but also it goes the other way. If the conclusion part's true, I can get back to the beginning. So this is a two-way direction. It's called a biconditional is actually what it's called. And so it's a biconditional statement that works both directions. If it has an Euler circuit, then the vertex of the graph has even degree. And if it doesn't, then it doesn't, right? Like this is how it's always going to work. And in fact, we could go back and we could take a look at this one and just check it. This one had an Euler circuit. We found one. So we know this has an Euler circuit. But we can verify, just sort of as a case example, that all of those have even degree. So let's check. Count the number of edges. Degree means how many edges come in and or out of, how you want to think about it, A. So how many edges connect to the point A? There's 4. Does everybody see the 4? There are 4 that come in or out of A. So that's its degree. We would say A has degree 4. How about E? There's 6. F? 2. G? D? C, and B. They're all even degree. Okay? Having even degree guarantees us that there is an Euler circuit. And we actually found one too, didn't we? We found an Euler circuit, so we actually saw that happen in this case. Now, there was plenty of things that were not Euler circuits that we tried and didn't work, but we were guaranteed that one existed. Okay, so that's what Euler's theorem is talking about. So we're going to take a look at another example where we're given it from the get-go, and we're asked to use Euler's theorem to decide if it has an Euler circuit. It's not actually asking us to find one, even if one exists. It just wants to know, does one exist? And we make that decision by doing what we just did for that last graph. We count the edges that come into each of the vertices. That is, we find their degree. So what is the degree of point A? 3. D? 3. C? E? We'll go there. E is 4, and B is 3. Whoops, I was writing that. 3. Okay, so there's actually quite a few of them that are odd degree here, right? But it wouldn't need to be a whole bunch, right? We wouldn't have to have a whole bunch of them having odd degree, but if we have at least one having odd degree, which isn't exactly possible, if one has odd degree, you have 2, but nonetheless, if you have at least one that has odd degree, it fails Euler's theorem, right? So is this going to have an Euler circuit? No, it's not possible for it to be done. So this will not have an Euler circuit. And the reason is because at least one, or you can say some if you want, at least one vertex is odd, is an odd degree. I need to move this up, sorry. At least one vertex has an odd degree. Should I try a different one? Okay. This one looks kind of like a bow tie, right? Now, the directions on this one don't actually match exactly the last one. There's more to them, so let's read through them carefully. It says, use Euler's theorem to determine whether the graph has an Euler circuit. That's just like what we did before. Then it says to determine whether the graph has a circuit that visits each vertex exactly once, except when it returns to the starting vertex. And then if so, write the circuit down. Okay, so first, it doesn't have an Euler circuit. Well, in order to do that, we can use Euler's theorem and we can write out the vertice degrees. So G is 2, I is 4, J, K, and H. Does it have an Euler circuit? Yes, it does. So our first sort of answer to the question, number 1, is that it does have an Euler circuit. Because all vertices have even degree. Okay, does that make sense? Okay, the next question then said something about to decide if the graph has the ability that when you do a circuit, you visit every point exactly once, except for the point that you go back to when you start out. Okay, so let's start at, you can actually start at either G, H, J, or K, and it would all be identical because it's a symmetric graph. So let's start at G and see what happens. If I go to G, where might you want to go next? H, and then I, and then J, K, and look what happens when I come back. I come back through J in the middle. Sorry, I in the middle again. And there's no other way I could have done that, right? Like I would have guaranteed have to pass through I a second time to get back to the other point where I started. So starting at G, H, J, K, any of those will cause that problem. The only other point that you could start at that would look a little different is to start in the middle. But if you start in the middle, what's going to happen? Same thing. You're going to go around one side of your bow tie, but you're going to have to come back to the middle to try to get to the other side. Right? So it's not going to have it either. Yes? So this one will not work. So where pencil goes. This one's is a no. You sort of question number 2. Starting, you could say no matter where we start. We'll say no matter where we start. We pass through I, that was in the middle, more than once. Okay, so let's talk about something called a cut edge. A cut edge is an edge in a graph whose removal disconnects a component of the graph. That is, its removal creates a disconnected graph. Okay, so once you have that written down, I'm going to draw you both an example and a non-example of graphs that have cut points, okay? So that you can see what those look like, or cut edges, excuse me, so that you can see what those look like. So this graph, it doesn't need to label the edge. Well, I do have them labeled, so we'll label Let's see. My points are big. Okay, there's an example on the left, and I have a non-example on the right. So let me talk about what makes these graphs different. Okay, so let's look at the example first, partly because I listed it first, but also because it fits the definition for what we're going to do. Do you see an edge that you could cut and make the graph into two separate disconnected pieces? BE, that's the most obvious one. If I were to cut this edge, it's like I would be taking it out. I would have two disconnected graph pieces, right? I'd have two components. So absolutely, that is one of them. So BE would do that. So my cut edges here, there's going to be more than that, by the way, but that's the most obvious one. BE is a cut edge. Let me show you another cut edge. That wasn't what I meant to do. That will be. AB is a cut edge. The reason AB is a cut edge is because the point A, that vertex A, is still a part of the graph that is now disconnected from the rest of it. I cannot get from point A to any other piece on the graph. Does that make sense? Okay, I'm going to put it back in now. So if AB is a cut edge with that kind of an idea, what other cut edges do you see? Yep, BC would be one. DG would be one. DE would be one. EF would be one. In fact, what did you just figure out? All of them are, right? In this particular graph, every single edge is a cut edge. Now, think about the second graph over there on the right-hand side. What happens if I take away one of these edges? It's still connected, right? And it doesn't matter if it was edge AB or if it was edge anything else, it will have the same overall image. The image changed, but it didn't disconnect from itself, right? So in particular, these places where you have cycles, right? That's what's going on there. There's a cycle going on there, are going to create places where you don't have cut edges. And things that don't have cycles, like in my first graph, was there weren't any cycles at all, create places where you are going to have cut edges. So taking a look then in example number 4, I want to pause for a second and give you an opportunity to write down all of the cut edges in your graph. So go ahead and list them, and then we're going to check and make sure everybody has everything listed correctly, okay? Okay, did you get any cut edges? You should have. Okay, good. What edges do you believe here are cut edges? EF, I agree. FC, FG. Does that look okay to everyone? I agree. We have 3 cut edges in this graph, and in particular, the reason that the other 4 edges are not cut edges is because they create a cycle. Right? Much like the non-example one that I showed you would have been a cycle as well. Okay, the next one that you're going to write down has got a lot of writing. We've got a couple more with a lot of writing today. This is called Fleury's algorithm. So Fleury's algorithm says that you start at any vertex and you go along any edge to any other vertex. It's very generic. Lots of any's there, right? Start anywhere you want and go anywhere you want. But when you go through that edge, you remove that edge from the graph. And then you keep going. The condition is that you do not cross and remove any cut edge unless there's no other choice that you have. You repeat this step until you have used all edges and returned to the starting vertex. Okay, so what in the world is Fleury's algorithm finding for us? Well, it's finding for us an Euler circuit. Okay, so in general, Euler circuits are not unique. Okay? And that kind of should make sense with the way that this was just described. You get to start anywhere and you get to go anywhere with one tiny little restriction. I mean, just don't cross anything that disconnects the graph unless you have to. Okay, so the idea that there's going to be more than one answer should feel reasonable. So what does this actually look like if you're doing this inside of my math lab? Well, it looks like multiple choice where you're verifying whether something works, right? We're going to do it from the front end of actually finding one the way Fleury's algorithm is written, because I want you to see how it works and to see that it does work. The one thing to be careful of if you're working with this inside of my math lab is that it might be a good idea to transcribe the graph you're seeing on the screen onto your paper to work with it, right? That might be a good idea. But be really careful when you transcribe the graph because you might miss a point or you might miss an edge or something like that. So just use some caution. So we're going to start with making sure that this graph looks like the one on your paper if you've printed something off. It looks like the one on mine. So I think I've got all the pieces where they're supposed to be. So just double check to make sure everything looks right if you've printed it off, or if you're drawing it in right now, be very careful as you draw it in. Now the directions say to use Fleury's algorithm to find an Euler circuit for the graph, and the only condition it has really is that it begins and ends at A. And it tells you there's lots of answers. So we're going to leave my notes right here, and we're going to do one together, but it's probably not going to match one I've ever done in my life before. I mean, maybe not. Eventually it'll have to, but you know. Okay, so we're going to start at A. And we get to decide where we want to go. And we can go anywhere we want as long as there's an edge to go there. So we're going to start at A, and where would you like to go? And as we go there, I'm going to erase the edge. If you're doing it on your paper, you can't really erase it. So if you have a color that you could use to color along it so you know that you've colored it, that would work too. So as we go from A to where would you like to go? A to G. Okay, so if we go from A to G, that edge is going to go away. And it literally disappeared off my screen, right? Okay, now we're at G. Where do you want to go? You have three options. You can go G to H, G to F, or G to J. Somebody pick one. H, thank you so much. G to H. That eliminates this one right here. Now we're at H. We do not have a choice. H only has one more edge coming out of it, right? So H is going to go back to A, which is just fine. So we're revisiting A, but we're allowed to do that, so that's not a problem. Now we're back at A. A has two choices. We can go A over to B, or we can go A down to F. Which one would you like to do? A over to B. Okay. So A goes over to B. B has lots of choices. B can go down to E, over to K, over to C, or around to D. Which one? E. Okay, so B goes down to E. Okay, that's still there. All right, so we've got B to E. Now we're at E. E only has one choice. E has to go to D. There's nowhere else to go, right? Sorry, I think I deleted something accidentally because the way it was drawn. Let's do those in there. Those are still there. All right, from D, I have three choices. I can go D up to C, D around to B, or D down to K, up to K, excuse me. Which one? C. I should probably make a mention. Notice I've disconnected my graph at this point, right? Twice. Do you see the lone little points sitting there by themselves? I have disconnected the graph, but only because there was nothing else I had a choice to do, right? So at the point when I disconnected that point from where I was going, I didn't have any other choice but to do that. Okay, where did we say we were going after D? C. Okay, so D is going to go up to C. So D went to C. After C, where are we going? Oh, we don't have a choice. We're going to go over to B. And notice that, again, I've disconnected my graph one more time, but there's no choice but to do so. B still has a choice. B can go actually three different locations, but there's one of them that you can't choose. Which one can you not choose to go to? You cannot do B to F. Why? It will disconnect the graph when I had other options, right? I cannot go B to F. If I did B to F, hang on, I would now have this graph and it'd be disconnected. And the reason it can't be disconnected and me continue is because then I'd be down here at F with no way to cross those paths. And an Euler diagram is, or not diagram, but an Euler circuit is supposed to cross all my paths, right? All the edges. And it didn't do that. So I can't go there. Do you want to do B to D or B to K? All right, I heard you both saying, everybody said one thing or another. Let's do B to D. It'll delete better, easier. So we go B to D. Where am I? And then D loses, we lose the choices, right? D goes up to K and back to B. You don't have any choices on that one. And then B will, in fact, come down here to F, right? Because at that point, that's the only place left to go. Okay? Now, I'm at F, and I cannot go where? Cannot go back to A. But I could go either to J or to G. We get to pick. Where would you like to go? G. Okay, and then I have everything else is forced, right? G has to go to J then, and J goes to F, and F goes back to A. So at that point, I have completely eliminated all of my edges. I've gone through all of them once, cut the graph all apart, and this created an Euler circuit. Okay? Now, we didn't check at the very beginning, though we could have. I do have the diagram down here in tiny form, but we could have counted all of those vertices, right? And check to make sure of their degree. They must have been even, or we wouldn't have been able to do what we just did. Okay, they were all even. Now, there are cases where we can find something else similar to an Euler circuit when we don't have all even degrees, and that happens in the following case. This is about an Euler path. So an Euler path is like an Euler circuit. It crosses through all of the edges, but it just doesn't start and end in the same place. So if you do not have all even degree vertices, but you have exactly 2 of odd degree, then an Euler path will still exist. Though clearly an Euler circuit will not, because they don't all have even degree. However, your path must start at one vertex of odd degree, and it must end at the other vertex of odd degree. So it does have a condition on it about where you start and end. With an Euler circuit, though the previous problem told us where to start and end, that was just the constraints of the problem. I could have started and ended at any particular vertex on the last one, and I would have been able to find an Euler circuit, right? They would have existed from every point. With an Euler path, with this condition, it will have to start at one odd degree and end at the other odd degree. Okay, you ready to take a look at one? We're close. Okay. So here's our diagram. If you need to jot it down, do so. We're going to determine whether the graph has an Euler path and justify why. We say it does or it doesn't. And if it does have a path, we're going to decide what the starting and ending point are. Notice it doesn't necessarily ask us to find that path, though we could, and maybe we shall, I don't know. But this question just asks us what the starting and ending places are. Okay? So how do we decide if it has an Euler path? We count the degree at the vertices. So what is the degree at A? It's 4. How about E? I think it's 6. F? 2. G is also 2. How about D? C? And B? 3. Will it have an Euler path? Yes, it will. So this one has an Euler path. Because there are exactly 2 vertices with odd degree. Okay, so the directions themselves just simply asked, what are the ending points and the beginning points then of such a circuit, or such a path, excuse me. Yeah, it must start / end, it doesn't matter which is which, at B or C, right? B and C are the ones that have odd degree, so it must start and it must end at those points. But finding it would look a lot like doing it for an Euler circuit. You just make sure you start at one of those points. You only cross through it if it doesn't create a cut point unless you have no other choices, and you would end at that other point that it lists. So let's do it really quick and find our Euler path for it, even though it doesn't ask for it, just because I want you to see that it does. Do you want to start at B or C? B. Okay, so if we start at B, where will we go? B to A. Cool. So here's B to A. Where do you want to go from A? A to what? E. Okay, so A to E. And then what? E to F. Okay. At that point, we don't have a choice. F has to go down to G and back to E. All right. Okay, after E, where do you want to go? Do you want to go over to B, down to C, to D, or to A? D. Okay, so E down to D. Now, and D doesn't have a choice at that point. We go back up to A, and then A has to come back down to C. So we're at C, and we cannot go C back to B. Actually, we could. We can go from C up to E, or we can go C back to B. Either way, it just depends on where we're going to start or end. So Which one would you like to go to next? C to B? I didn't mean A, I meant E. I think I just said the wrong letter. Yeah, I said the wrong letter. C to, what did we say, B? I think so, C to B. And then once I make that decision, then the rest of it's determined for me. B goes to E, and E goes to C. And we see, in fact, we started at one B, we ended at the other C. And again, these are not unique. We made decisions along the way several times where we had more than one choice. Occasionally on some graphs, they might be unique depending on the graph itself, but usually we have more than one choice at each opportunity.